My name is Bo Gerlach. I have been with the company for many years, and I have also been dealing with safety problems which concern gas, because this is a gas manufacturing company and we are dealing with industrial gases. When you hear the word gas, normally people are a little bit afraid. They think of dangers, they think of explosions. But you must remember that gas is everywhere and that the air we are breathing really is a gas. Or, well, it consists of several gases. 78% of nitrogen, 21% of oxygen, and about 1% of argon. In this room, I have just taken out 1 cubic meter of air. You can see it here. It's 1 cubic meter. It's so that many a time it's difficult to have a feeling for how much is 1 cubic meter. Gas can easily be kept in a balloon, but in a balloon there is almost no pressure and therefore not much gas. And therefore transporting and selling great quantities of gas is not possible that way. However, when you see tanker trucks on the road, there is a very special feature. They contain gas in the liquid state. 1 liter of liquid nitrogen may later be made to transfer into 680 liters of gas. Such liquefied gases are very cold. Liquid nitrogen, for example, is very cold. It's about minus 196 degrees. Now I'm pouring out liquid nitrogen. And you can see on the table the cold gas is not lifted up. It's floating over the surface of this table. The cold gases, as we said, were traveling downwards because they are heavier than air. And we thought it might be interesting to see something which is unique. Everybody knows what a waterfall is. This is a nitrogen fall. Nitrogen is not poisonous, but more nitrogen in the air than 78% will displace the vital oxygen, creating a dangerous oxygen deficiency. And now what I'm going to show to you is what happens if nitrogen is traveling down into a pit or a cellar or something which is low, a low point somewhere on the floor. I'm lighting this candle here, and the candle burns in normal air. It's using the 21% we have in this air. And in my small aquarium here, there is also just plain air. And now I'm taking nitrogen, but in the liquid form. And you can see it floats over the edge of the beaker. And now I'm taking this beaker and placing it inside my aquarium. And you saw immediately what happened. The nitrogen was going down and extinguished the candle. Extinguished life, so to say. Well, now you saw what happened when the liquid nitrogen entered the aquarium, went to the bottom, and expanded from liquid into gas. So you can see I really mean expand, because it's a very large quantity of gas you get from a small quantity of liquid, which is very good, because when you are distributing these cold gases, you can have them in a tanker truck. Some words for caution are needed, because it expends to very much gas. As you can see, when I now pour this nitrogen into the jar, and now I will be closing the jar. And now you can see what's happening. And I know what's happening. Well, you will agree, lots of gas. And also, when designing gas systems, you should remember that never close in liquid in between two valves. Never trapped liquid in between two valves unless you have a safety valve there. These liquid gases in the liquid state, are very cold. We are speaking of very low temperatures in the order of 183 degrees Celsius for oxygen and minus 196 for nitrogen. These temperatures are low and can preserve, for example, food, and they also contain, the liquids contain such large quantities of cold that you can cool down things very rapidly, and also you can cool them down without losing the fine texture, as, for example, you look at this flour here, and I'm pouring liquid nitrogen over the flour. Just for this short while in the liquid nitrogen. And it's still looking like the same flour we had before, but it's not the same flour. It's very brittle. These cold liquids are excellent for preserving food, like vegetables, meat, fish, shrimps, and so on. But let's consider what could be happening to a living tissue like the human skin, because permanent injury might be happening very rapidly. We like to remind people who handle cold liquids that they always should keep their trousers legs outside their boots, because if the trousers legs are inside the shaft of the boots, liquid spillage might enter and you might not be able to get your boot off rapidly enough in time. And now we imagine these are your toes. Now this is something which is more or less extreme, but we may use this just to teach people to be very careful. Many materials will get hard. It's not only that we saw that the sausages and the flour, but also metal will be solid, as this lead bell here. You can hear it does not sound, it does not ring. It's rubber and lead. And now I'm going to put this bell down into liquid nitrogen. and wait and see what happens. You see, at low temperatures, the molecules, even in metals, contract. The lead bell had shrunk. This is a physical effect we can make use of in an interesting technique in joining parts together. To show you an example, I have a shaft and I have a disc, and this hole is milled so that it is slightly smaller than my shaft, and it can't get onto the shaft can't enter. And now we will see what happens when I cool the shaft down into this vessel with liquid nitrogen. So let's now see what happens. And now I have got a joint, which is very good, and I did not use any methods like welding or heating. When the temperature has evened out, these parts will be firmly joined together. Electrical resistance in conductors may entirely disappear at extremely low temperatures. Also, magnetic fields are influenced, and special ceramics may enter superconductivity at minus 185, the so-called Meissner effect. We have this little container here to give us the possibility of cool down the ceramics, and I have here a small magnet which I will put on top of this. As you can see here, nothing happens really now because the magnetic field of this magnet is penetrating the ceramics, and there is no effect of attraction or nothing else. Now you see what's happening. The magnet is floating freely above, and this is because that now the magnetic field cannot penetrate the ceramics, and the ceramics now has generated a field of its own which is opposite to the magnetic field of the magnet. As you will remember, we had 78% of nitrogen in the air and 21% of oxygen. Now, I will show you what oxygen looks like when it's liquid, and I will also show you the property of oxygen to enhance any fire. Oxygen is needed to burn things, and when we have much oxygen around, things will burn very much. Now here you see this is liquid oxygen, and you can see the slight blue color. And now I here have just one ordinary wooden stick, which I'm setting fire to. And you see it's this very small flame burning, and when I take this small flame and go down in the pure 100% oxygen atmosphere, you can see how fiercely it starts to burn. And in the inert gas, I can get this to extinguish. When I'm very quick, I can show this very funny effect that this is just glowing, and it ignites, it goes out, ignites, goes out, ignites. A little bit of glow left is just sufficient to make things burn, and as you can see, it burns fiercely down in the oxygen. So the wooden stick would burn fiercely in the oxygen, and this was a very concentrated atmosphere. We were above liquid oxygen. Now, imagine that the oxygen in this air in the room or elsewhere where we are working is just enriched. This means some % more, which might be the case when welding in a closed, confined area or when we have a spillage of oxygen. And imagine now that you enter with your clothes burning. I will show you an example. And I'm pouring some oxygen down here into my aquarium. And now the oxygen is boiling out there, mixing with the air, and also at the same time now pushing out the nitrogen. So we get an oxygen-enriched atmosphere. And you are very unhappy because your clothes were burning. And now you see what happens when you enter this room. So you had better not enter this room. Now you will see the same effect, but more or less real size. Even protective clothing made of cotton like this are not combustion-proof, but will therefore have to be chemically treated to be resistant against flames and to retard ignition. However, you will have to remember that laundry will remove this agent and treatment of the fabric will have to be repeated. Now we are testing what is happening when we enter an oxygen-enriched atmosphere and then expose the clothes to sparks and molten metal from a cutting operation. Here we now simulate a large oxygen leak, and we see that the oxygen concentration in the confined working area is climbing to about 38%. We start cutting from outside and thereby inside drenching the clothes with molten metal. You can see they do not ignite immediately, but when they start to burn, they burn fiercely. You can see that this working shirt has taken up more oxygen in the thicker seams. And here is a woolen sweater which is partly synthetic. All the microfibers on the surface help to spread the fire, and remember that synthetic fabric is dangerous. It not only burns, but will melt and cling to the skin. Hydrogen also is an interesting industrial gas. It is produced by a process called electrolysis. And hydrogen is a very friendly gas when it comes to environmental conditions. For example, if you run your car on hydrogen, it will only produce water as the waste product in the exhaust pipe. And I now have here hydrogen gas. I will open this. You can hear the hissing noise. And now I will also show you that I can blow a balloon with hydrogen. Well, there the hydrogen disappeared. Hydrogen was lighter than air. And when hydrogen burns, as I already said, it forms together with the oxygen in the air water. But there is another property which might be hazardous together with working with hydrogen in an installation. Let's say now in the factory where they make the hydrogen. If we have an accident that something breaks and hydrogen escapes and hydrogen is ignited, then we have a flame which is almost invisible. And now the flame, as you can see, burns almost invisibly. There might be some specks, a little bit of dirt coming together with the flame, but if you are in a hurry and walk into a room, you might not see it. And now I can demonstrate what happens. Now you see where the flame is. We are back in the training field, and now we ignite hydrogen. The object of the training is to teach people that the important thing in most cases is to find the source of escaping gas and just shut it off. You don't always need a fire extinguisher to get close to the flame. Just good gloves and quick action. And, of course, do not be afraid of the roaring noise. Gases are influenced by temperature, volume and pressure. Compressed gas becomes hot. You can feel compression heat in your hand holding a bicycle pump when pumping air into your tire. And if I now make a good insulation so that the heat cannot be transferred to the surroundings, to the ambient air, or if I'm very quick doing this and I do not get the air out of the pump, everything stays down there, I will get a very high temperature. Would you expect that I am able to ignite oil just by mere force of my hand, pumping ordinary air in this room? I will show you what happens. Here now I have my bicycle pump. Well, in this case it's a glass tube. And this glass tube now contains air. Well, I will be real sure to have air, which means that I'm pumping down the air of this room, because what I need down there are those, as you know, 21% of oxygen. Oxygen is needed for any combustion. Now I'm pumping down here, hopefully having fresh air down. And I'm standing this in the shield so I will not hurt my hand in case I break the glass. At the end of this piston, this is a long rod and works like a piston with an O-ring, I have attached a bit of cotton, and this is just to carry my oil. Now I'm entering here, and what I'm going to do now is I'm rapidly, and most rapidly, as fast as I can, pushing down the piston, and you look down here and see what's happening here. You saw my hand power was enough to light oil, and I was there, well, around 50 bar, and I get a temperature of around 500-600 degrees Celsius. Adiabatic compression can also happen when high-pressure gas is entering a low-pressure system, like here when 200 bar of oxygen enters an atmospheric pressure-filled pipeline, and when the valve is opened rapidly, we get a burnout at the end. Now let's look at acetylene. Acetylene is a high-energy compound consisting of carbon and hydrogen, and acetylene is different compared to other gases because it is a combustible gas which may decompose. That means that it will fall apart into its atoms, carbon and hydrogen, releasing large amounts of energy. And there is no oxygen needed as in other combustions. Accidents during the years have proven that it is impossible to store acetylene under pressure in larger hollow spaces. One measure to prevent this was to fill the cylinders with a porous mass. Now, here you see is a small acetylene cylinder. And this acetylene cylinder is not empty. It's filled with a porous mass. And when I say porous, I really am speaking about pores, because there are cavities, very, very small cavities, millions of them. So if I now would compress this porous mass, I would just get something like this. So there are these pores, and also there's another feature which has been invented. To get more of the gas inside, we dissolve the acetylene in acetone. How easily acetylene is dissolved in acetone can be shown by a little experiment. At first we are filling a glass flask with acetylene gas, and then dipping down the opening into a beaker filled with acetone. Now, at first, a little slowly but faster and faster, the acetone is climbing up into the glass flask, dissolving the acetylene, eventually filling all of the glass bulb. You can see it here. Now we are emptying the flask again. And now I can ask you, is this still the same acetone as it was before? No, it's not. This acetone contains acetylene gas. And this means also that when I have such a cylinder and it's empty, it is not empty, because you still have the solvent in here very evenly distributed. There is the gas dissolved. So everybody should remember that an empty acetylene cylinder is not to be considered empty. When we ignite this acetylene gas full pressure, we get a roaring flame. And notice, already after such short time, the end of the tube is sufficiently hot to ignite the gas over and over again. That's an important matter we will return to shortly. Also here, we would like to shut off the gas supply, but the flame is very hot. And in order to get close to the valve to do that, we kill the flame with a powder extinguisher. And now, of course, we have to rush to close the valve. In open air, there's no problem, but indoors, there is more to it. You will have to use your judgment, because if you allow unignited gas to escape, you may cause a room explosion. Acetylene reignites very easily. Here I'm heating a piece of iron, and now the thermometer shows not more than 350 degrees. I'm now pointing acetylene against this piece of iron which I've heated. You cannot see the temperature, but Still, the acetylene will ignite. As we said before, some of the gases are lighter than air, some of the gases are heavier. When we come to the problem of combustible gases, it is rather dangerous when they are heavier than air because they will travel downwards, they will collect in pits and cellars, they will collect down in your boat when your camping stove suddenly doesn't burn, and so on. So it might be interesting to see what happens if I now pour out propane into a beaker and pour it down a slope. And I'm now pouring the propane down this tube. And as you can see, it ignites all the way down and all the way back. What I'm now going to show to you is what the different mixtures can do and how small an energy we may also need just to set off the explosion. And here is a small vessel. It's a volume of about half a liter, and on one side you see there's an ordinary spark plug, so I can produce a spark inside. And to get higher energies working on the other side, I have a coil which I can get to glow, so it will be some 100 degrees there, and also much more heat capacity. Now, I will put a lid, it's just a plastic lid, on that tube. So now it's closed and filled with air. What I can do now is I add, by means of this syringe, a certain quantity of combustible gas and try out what's happening, spark or coil. So now I'm taking this nozzle here, and here we have just only acetylene, and I'm taking the syringe and filling the syringe with 20 milliliter, adding this to my box, and just to get a good effect, I take another one, and let's take a third one. So, when I now empty this, I've got a mixture in there of 12% acetylene in air. Let's see what happens now if I press this handle and get the spark. Now for another test, we will take propane and we will just take one syringe. This are now 20 ml, 20 milliliters in half a liter of air. And now we will try the spark again. You see? Nothing happened. The spark was too weak, not much energy. But now I'm taking a little more energy and taking my coil. In the first stage, we have to prevent leaks. If it comes to worse and we have a flame, we should try to stop it. We don't want more gas to enter the combustion area. This is propane gas at full pressure leaving a cylinder. Propane is in liquid state in these cylinders. As long as there is some liquid inside, we can take out gas. The pressure depending on ambient temperature. Now we are going to pour out some of that liquid into this bucket. The white mist you see is water condensing at the outskirts of the escaping gas, because the gas is rather cold. Now we have collected a suitable quantity within the bucket, and you can come and look at it. It is not boiling very much down there in the bucket because the temperature of the bucket itself now also is low. That the liquid is cold we can prove by immersing a flour. The liquid is not as cold as liquid nitrogen, but the temperature is sufficiently low to deep freeze the flour. We throw a burning match into the bucket. The vapor above the liquid catches fire, and now you see what happens if you throw water on top of it. That is exactly what happens to your deep frying oil if it catches fire on your stove. Instead of getting the fire out, you are spreading it over a wider area. Now we are turning the bucket over and emptying the rest of the liquid, and you see it converts to a large cloud of burning gas. Here is a demonstration of an efficient safety feature. When you are connecting your gas stove to the cylinder, you will use a pressure regulator. And this unit also incorporates a quick-shutting valve. It senses sudden changes in gas flow. If you now here happen to burn your gas hose right through, the sudden pressure drop and the sudden increase in gas flow will entirely stop gas supply. Here you can hear the click. Now we have turned propane cylinders to lie flat, and now liquid is coming out. Again, the mist indicates the borderline of gas and water vapor. We try to find the gas phase here. Now all the gas burns and the rest of the liquid adds to the fire. Here we should realize that liquid propane turns into much gas. 2 liters of liquid will result in 1,000 liters of gas. Remember, never transport propane cylinders lying down. The safety valve will not be able to safely handle liquid. You will get an enormous amount of gas. Here again we have a flame of gas from the gas phase. The students are told how to extinguish the flame and also the importance of immediately closing the valve. Here we now have one of those small camping gas cylinders. There is no safety valve, which makes them special. When heated, the pressure of the liquid inside will cause a hydraulic rupture, and all of the liquid gets out at once. It is a nice but very dangerous fireball. So, although small and seemingly harmless, you must avoid getting those cans near to any heat source.